Good evening, everyone, and welcome to our final session of the fourth day of Varsity Sci. This session will be moderated by Garrett, who is the president of the Cambridge University Chemistry Society. And I will now hand over to Garrett for the rest of the session.
Thank you. Christoph, good evening, everyone. As he said, my name is ChemSoc. For Cambridge staff and students, ChemSoc will be holding talks online around this time during term, so hopefully we'll be hearing more introductions from me over the next few months. This Varsity Sci session is focusing on physical sciences and medical physics. Our first speaker is Pip Knight. Pip is a student of natural sciences at Cambridge and will be outlining some nanomaterials which will possibly help in the future to reduce our reliance on fossil fuels. Pip, over to you.
Hiya, thanks Gareth. So yes, I'm going to be talking a bit about nanotechnology and the ways in which some of the more innovative methods can help us to live sustainably with our planet. So a bit about me. As Gareth said, I'm a natural sciences student. I'm going into second year, and my specialism really is materials science. So this talk is based around things that I've read or written about or talked to people about. So it's just a bit of a compilation and a little introduction for everyone. So yes, we're focusing on innovative ways to generate energy that perhaps aren't the classic renewable technologies that we know and love. So I will kick us off by talking a bit about nanogenerators. So nanogenerators harness their energy from a bit of an unusual source. So they harness it from ambient vibrations, which can be anything from sound waves or wind or engine vibrations, anything that vibrates a small amount, basically. And they can be piezoelectric or triboelectric. And anyone that has studied a bit of material science will, I'm sure, be very familiar with both of these, but I'll give you a bit of a brief overview anyway. So piezoelectric materials harness these vibrations so basically you've got your sound wave coming along or whatever thing is making your material vibrate, and that introduces an oscillating strain in your nanogenerator. And at the unit cell level, this strain causes the ions to change their positions, and the new minimum energy position happens to have dipoles present. And if you have a single crystal, all of these dipoles will be aligned, and overall you'll get a polarity in your crystal. And that's what causes the voltage. And the fact that this strain is time varying because you've got this vibration from your sound wave means that the voltage is oscillating in time, which is the basis of an AC voltage. So that's how the piezoelectric ones work. And triboelectric, you should be very familiar with, because this effect is exactly why your hair will become static when you rub it with a balloon. So it basically is the transfer of electrons between dissimilar materials. So they have different affinities for electrons. So in a nanogenerator, when they come into contact, when they rub, you'll get a flow of electrons around a circuit, and that's where you get a current from. So nanogenerators they've been receiving a bit of press recently. Yeah, they've become a lot more popular, and they're believed to be a very important part of what's called the Internet of Things, which is quite a buzzword in technology. To explain a little bit about it, I'll quote Matthew Evans, who's the Internet of Things program head at Tech UK. Simply, the Internet of Things is made up of devices, from simple sensors to smartphones and wearables, connected together. So what he means by this is they don't need any human intervention. All of these sensors and generators and things actually causing effects in your household are all connected together, and we don't need to put in any input to make it all work. And finally, I would just touch on some key research going on in Cambridge, led by Sahini Karnarayan. He's a very lovely lady, and she works on triboelectric nanogenerators, mostly made of nylon. And if you want to read a bit more, I thoroughly recommend giving her a Google and reading some of her papers. Great, so next up, I will talk a little bit about nanoplasmonics. Again, this should be a reasonably familiar thing from our daily life, because so-called surface plasmon resonances occur in bulk metals as well as nanomaterials, and it's why metals are shiny. So basically, we've got our light waves coming along, and they're causing the electron cloud to oscillate as a whole, which absorbs the energy of the light and then re-emits energy, which is why we get that reflection. But if you take that effect and put it down to the nanoscale, you're localizing a lot of energy in a very small volume. So you've got a really high surface area to volume ratio, which means that we can absorb a lot of the photons, but localize it in a very small volume. So yeah, they're great energy absorbers, which is why we've used them previously in things like cancer therapy to kill tumors by heating them up from the inside. But the exciting implication for the environment is the fact that the resonant frequency at which these nanoparticles, the electron density will oscillate, is very much tunable by the size of the nanoparticle or what it's made of, so which metal you're choosing, most commonly gold and silver. So this means that we can pick up the specific wavelengths of light that are often missed by photovoltaic cells, which is very useful and makes them much more efficient. So that's the general idea, and it's still fairly early stage research, but it's quite exciting. And if you would like to read more about it again, Emily Ringe is a good place to start. She leads the Cambridge Research Group, and there's also a great paper here about photovoltaics and plasmonics. So there we go. And finally, I'd like to talk a little bit about phase change materials. So phase change materials can provide insulation and temperature regulation. And examples of these are salt hydrates. And the basic idea, the science behind it, is that they absorb heat when it's higher than the temperature that you want your system to be at, and then they melt. And then when it gets a bit cooler, they will refreeze and release that latent heat. And that's a mechanism quite commonly used in nature. But the issue is, if you're wanting to do this using a bulk material, so bulk salt hydrate, you'll tend to get issues with very slow freezing and also inhomogeneous freezing. So it's very difficult to get everything at the exact same temperature, and you'll find certain parts of the liquid will start to freeze before others, and ice has a tendency to freeze in a pure form, so that leads the rest of the salt hydrate to have a different hydrate number, and that changes up the chemistry bit and means that it will solidify at a different temperature, which makes very precise regulation quite difficult. And that's where nanoparticles come in, because we've got the same surface area volume ratio that we were talking about before, which means that they freeze very quickly. And also, generally, when we're talking about nucleation, we're talking about an energy balance between the energy that's given out by freezing, in terms of the Gibbs free energy, and the energy cost of making the interface between the solid and the liquid. But in the case of a nanoparticle, it's very much like it's so curved that that surface is actually very small. It's just the middle bit of a hemisphere. So that's not a very big energy cost. So they freeze very, very quickly. And we don't get any of the issues with hydrate number changing. So the design is in this paper that I've written down here, and it's essentially a capsule. So you've got the salt hydrate inside this silica capsule. And silica is great because it's inert and it's really conductive. So again, I really recommend giving that a read if you're interested. And there we go. So that's like a whistle-stop tour through some exciting materials that I've been reading about. But I am very open to any questions if you'd like to hear more.
Thank you very much, Pip. That was a real tour de force, and as you said, just brief tour around the things happening in nanomaterials. As a reminder, if anyone has questions, then feel free to share them in the Zoom chat or unmute yourself on Zoom, or also write in the YouTube comment section. So I'll just kick off and start with a question by asking, how do you think these nanomaterials are first discovered? And how do we know that they are going to be effective? Do we look mainly at their composition? Do we look more at their design or their structure in space?
So I think a lot of the time you start with a bulk material, and you think about the issues associated with it. So the third example there is a very good way of demonstrating that. So we've got that issue with the freezing, and we know that chemically it should work. Like, there are plenty of plants that use this latent heat mechanism in order to regulate their temperature. But you see those issues, and then from the basic ideas behind nanoparticles, you can quite often see that that's applicable. And then I think it's basically experiments from there in terms of fine-tuning it to make it a really effective system. So these researchers found that that specific capsule design worked pretty well, and was quite efficient.
Yeah, it's very interesting, as you say, kind of the relation between the bulk material and the kind of materials of interest that you're looking at.
Definitely.
We've
Yeah.
just had a question come through. Would you mind elaborating a bit more, if you could, on the role of nanomaterials in cancer treatment? With our next talk actually also focused on the medical sciences, it might tie in quite nicely.
Yeah. So I'm not much of an expert. Obviously, I'm a second year undergrad, but from what I understand, it's that idea about localizing a lot of energy in a very small volume, and you just generate a lot of heat, which heats up the tumor and kills it, hopefully. Fingers crossed.
Yeah, it's an interesting mechanism. Actually, it's something I don't know much about myself, but
Yeah,
I mean, I'm
it tends
sure
to be
these.
gold and silver that are used,
Okay.
because they're inert. So yeah.
Very interesting, because I mean, these papers that you've mentioned as well, I'm sure we could share on Facebook and on the relevant pages
Yeah,
afterwards, because
definitely.
I also I'd really be interested in reading them. Going back to some further questions, do you think you could give some examples of where phase change materials are used in our daily lives?
So there's a plant that I can't remember the name of. It might be lobelia something, but it like exists in sub-zero temperatures overnight. And basically it has this like central cavity that's filled with water, I think, or some liquid. But the basic idea is that that's acting as the phase change material. So it's freezing overnight, but quite slowly, and releasing that latent heat to mean that the important cells all around it don't freeze, and that's how it stays alive in that cold environment.
Yeah, so it's seen in nature as kind of manifesting in different ways, and there's ways in which that we can also use it ourselves in positive ways, which is, yeah, that's really cool. To ask another question, what would you say are the main factors kind of limiting the creation of these nanomaterials? Are we limited by the methods, the supply chain, or the materials just generally?
Yeah, I would say there is quite a significant issue in that the best or the most well-researched nanomaterials, for example, in the plasmonics case, are gold and silver, which is not particularly sustainable because obviously it's gold and silver. There's not much of them, and they're very expensive. But over the last few years, there's been a lot of research into alternatives like magnesium and aluminium. And if you want to read about Emily Ringer's research, she does quite a lot of work on those more new materials, but we don't understand their behavior quite as well yet. So obviously it would be a while before they'd be used in like medical applications, especially obviously since they're more reactive. But in terms of the photovoltaics, I think that's an example where they would potentially, we might see them in the future.
Yeah, and would you say that kind of photovoltaics are the perhaps most important? Do you think it's most important in energy, in medicine, or, you know, they're all very useful things, and the fields will develop in different ways, but
possibly I would say photovoltaics is the one that needs definitely more research. That is very much early stage, and there's quite a lot of ideas surrounding photovoltaics. So I don't think this one will necessarily like, it's not definite that it will take off hugely, whereas nanogenerators, I think it is widely thought that they will be very useful. I mean, I saw an article a couple of days ago in the Times about like charging mobile phones by going on a walk with your nanogenerator and like your arm swinging, and I think that has like a very obvious application, and big tech is quite interested in it. So yeah.
Yeah, as you say, the kind of the piezoelectric and triboelectric things that can be used, and yeah, I mean, there's so many possibilities for it, and I think it's very positive for science moving forward, and really showing kind of the interdisciplinary nature of material science, really, and it's something that this symposium has been, trying to achieve, and it's something that you've really been showing perfectly. To come through with another question here. Do you think that any of the materials you've described could play a role in designing brain-machine interfaces? This question asker has heard that this is a material science problem, really, and would be interested to hear your take on it.
I have to say, I don't want to come up with nonsense in this case, and I don't know very much about brain-machine interfaces. I'd love to hear if you'd like to drop me an email and tell me all about it. But yeah, I don't know very much about that.
Would you like to just tell everyone your email, remind them again if they want to get in touch with you after the talk?
It's pjk58@cam.ac.uk.
Great. Thank you very much, Pip. That was a really interesting talk. We're now going to move on to our second speaker, who is also a student of natural sciences at Cambridge, Helen Yan. Her talk is focusing on using the photoacoustic effect to visualize tissue, and it sounds like a real combination of physics and medical science. She's also going to compare Monte Carlo simulations, which are currently used in the tissue field, and as a chemist, that's something that particularly excites me. So, Helen, the stage is yours.
Thanks, Garrett. Just gonna share my screen. Right, so hi everyone. I'm Helen, and I'm a second-year undergrad studying natural sciences at Cambridge. So I'll be talking about my summer project, which I did with the Vision Lab at the Cancer Research UK Cambridge Institute. And this project is about using machine learning neural networks to quantify lipids and oxygen saturation from photoacoustic imaging data. So this is the overview of what I'm going to talk about. So I'll start off by giving some background on photoacoustic imaging as well as machine learning. And I'll then move on to talk about my method and procedures, in particular, the training data I used. And then I'll go on to some results, both in silico and in vivo, and I'll finish off with some conclusions and comments about future work. Okay, starting off with the background on photoacoustic imaging and some machine learning. So photoacoustic imaging is based on the photoacoustic effect, which is when you shine light onto something, this light gets absorbed. There is a temperature increase, thermal expansion, which is followed by a pressure change, and that emits acoustic waves, which can detect. There are a lot of different systems for this type of imaging, and shown on the right is an example. So light coming in from a laser and then onto an animal, could also be human tissue. And the signal gets detected by a computer, and this computer can then reconstruct an image. So when we image using a lot of different wavelengths of light, we get a photoacoustic spectrum. And from this spectrum, we want to get tissue properties such as blood oxygenation. And this photoacoustic spectrum is really made up of constituent spectra from different chromophores in the tissue. So chromophores are essentially light-absorbing molecules such as hemoglobin, water, lipids, collagen, etc. And the conventional method for doing this is using an algorithm called spectral unmixing. And this algorithm assumes a linear combination of the spectral signatures of these light-absorbing molecules. However, this assumption is invalid and really gets problematic with increased tissue depth. So in my project, I'm using machine learning instead to do this spectral analysis and getting the tissue properties. And the point is to improve the results. And so the properties that I've been interested in are total hemoglobin, which is the sum of oxyhemoglobin and deoxyhemoglobin, oxygen saturation, which is oxyhemoglobin divided by total hemoglobin, as well as lipid coefficient, which is the concentration of lipids divided by concentration of water. And so why do we use photoacoustic imaging? Why is it good? So the applications mainly lie within cancer detection, because as tumors form, there are reformations of blood vessels. And because photoacoustic imaging picks out on the optical properties, we can target hemoglobin, which absorbs strongly. So here are just some examples of images taken with photoacoustics. So there's a mouse ear with some nice blood vessels, mouse brain, as well as some tumors encircled on the bottom right. Okay, leaving photoacoustics for a bit, now on to machine learning. So machine learning is an application of artificial intelligence, and it uses patterns to make predictions. So there's no need for actual programming of these algorithms, but instead machine learning relies on having large amounts of training data representing a lot of variations of cases. And so examples of applications include prediction of house prices, face recognition, object classification, and what I've been interested in, quantification in biomedical imaging. I also want to talk about neural networks, which are part of machine learning. So in general, we have an input layer, which is where we put in our pattern. In this case, it could be a picture. And then there are hidden layers connected to the input layer and to each other that can pick out features. So in this case, you see it goes from identifying rougher features to then like nose and eyes, etc. And then finally, we have an output layer, which gives us the prediction. In this case, George. We could also have outputs corresponding to different people here. Okay, that's it about the background. Now let's move on to the method. So the training data I used to train my neural networks were all simulated. So on the right here is an example. It's a skin phantom, and phantoms are basically stand-in for human tissue. It's a cube with 1.2 centimeter sides and 200 pixels along each dimension. And it has different regions, coupling layer followed by epidermis, background layer 1, we have a blood vessel, and then background layer 2. So to try and get representative training data of real skin, in essence, the blood vessel oxygen saturation was randomly varied between 0 and 1 for these 200 phantoms. And then the background layer 1 lipid coefficient was randomly varied between 0 and 3. And here is an example showing the relative absorption in the phantom. So the light transport was simulated with the Monte Carlo simulations, and we had light of wavelengths 700 to 1,000 with increments of 15 nanometers. So that gives a total of 21 wavelengths. And then the absorption was recorded. Yes. So to get the data and make it possible to then feed into a neural network later, I process it by first taking the 3D phantom and then summing it along the vessel, so make it into a 2D slice. I just want to show here that the photoacoustic spectrum for each region can be quite different, so it's shown on the right. And also on the bottom left, you can see that even though pixels are from the same region, like the vessel in this instance, they can have different shapes. And this is what we're trying to, this is the pattern that we're trying to predict on to get the tissue properties we want. So out of the 200 phantoms, 198 were used for model development, while 2 were left for evaluation, which I will talk about later. So the 198 2D slices times that by 200 pixels in the X direction, 200 in Y direction, gives me around 8 million of these pixel-wise spectra. So that's a large enough data set for machine learning. This set of roughly 8 million pixel-wise spectra were then randomly split into training, validation, and testing data sets in ratios of 64, 16, and 20%. These pictures are just to illustrate the neural network architecture I used for the quantification. So for both blood oxygenation and lipid coefficient models, there are 21 nodes in the input layer. So each node corresponds to the absorption at one of the wavelengths. So there are 21 wavelengths. And the hidden layers, don't really have to bother too much about that. It's just that I used this because it turned out to give pretty good results. And the output layer is consisting of just one node because there is really only one value we want to predict each time. So either the oxygen saturation or the lipid coefficient. And here, shown here is the loss against the number of epochs during training for both models. And loss basically, so the smaller the loss, the greater the accuracy of the predictions in essence. And epochs, that's the number of times the data set passes through the neural network. So as you can see, it decreases quite nicely. Okay, now moving on to some results, both in silico, which is the computer generated data, and in vivo. So if you remember my data set of around 8 million pixels and a test set of 20% of that, these are scatter plots showing the predicted oxygen saturation or lipid coefficient against the ground truth. So on the top, I've used the conventional spectral unmixing, which I said had a problematic assumption. And on the bottom are the neural networks that I created. So, well, yes, there is a greater spread for the spectral unmixing in the blood oxygenation predictions, deviating more from the ground truth, which is basically shown by the line going across. And here are scatter plots again. This time it's relative estimation error against ground truth. So relative estimation error is just the estimated value minus the ground truth divided by ground truth and times 100 to get percentage. Again, more spread for spectral unmixing, and that is really shown on the box plots at the bottom, as you can see, comparing the conventional spectral unmixing to neural network. So yeah, if you remember, I had 2 phantoms left out for evaluation. Here they are. So on the top row, we have ground truth for both oxygen saturation and lipid coefficient. And the middle row shows the neural network predictions, while bottom shows spectral unmixing. So as you can see, the neural network predictions are closer in resemblance to the ground truth. Yeah. And here I have picked out regions of interest. So for blood oxygenation, I picked out the blood vessel. And for the lipid coefficient, I picked out the background layer 1. And it's again on the 2 phantoms shown on the previous slide. So as you can see, the vertical dashed line shows the ground truth. So the spectral unmixing on the top row again shows greater spread and also sometimes further away from the ground truth than the neural network at the bottom. Right, moving on to some in vivo data. I just want to mention that I only did blood oxygenation prediction, not lipid coefficient for the in vivo data. And this is because lipids don't absorb light as strongly as hemoglobin, so it can be difficult to predict. So the images on the left show cross sections along the length of a mouse. And these are all taken at 800 nanometers, which is where hemoglobin absorbs quite strongly. So we can get nice images. And I have picked up one slice where you can see the aorta quite clearly, which is the light little blob towards the middle. And on the bottom, that's the image showing the total hemoglobin. And total hemoglobin can be used as sort of an indicator of signal to noise ratio. So we know, like, physiologically, we can't have negative total hemoglobin. That doesn't really make sense. So and on the color bar of this bottom image, you can see that there are negative values, and so that's is probably not great signal there. Yeah, and then further on the right is just picking out the aorta specifically. Right, so the predictions are shown here. So again, spectral mixing on the top, neural network at the bottom. So because of the signal to noise issue we have and having negative total hemoglobin, it's doesn't really make sense to predict on the whole image. So the predictions are only made on regions with high total hemoglobin, and those regions are shown in red on top of the black and white images here on the left. And you can see, looking at the color bar, that actually both spectral unmixing and neural network gives quite physiologically reasonable results, 0.9 to 1-ish, which is what we expect in a living mouse. And further picking out the aorta and predicting just on the region here, we can see that the spectral unmixing has a greater spread of predicted values compared to neural network, if you look at the histograms on the right. All right, conclusions. So in silico, so in the computer generated data, we can say that neural networks are better at predicting oxygen saturation and lipid coefficient than spectral unmixing. And neural networks are also able to predict reasonable, physiologically reasonable results on in vivo data. And so the accuracy of neural networks on real life in vivo data is quite strongly dependent on the training data quality. And what I mean by that is that so we couldn't predict on the whole slice of the mouse. And well, because the training data essentially had quite nice symmetry and geometry with a clear signal. But there is a lot of potential for neural networks in photoacoustic imaging. But before we really can deploy that or have that in use, there are future work that needs to be done. So first off, we could validate quantification. So we couldn't do that with the mouse. We don't actually know exactly the blood oxygenation in the mouse at the time. So instead, we could have a blood phantom. So a real phantom with blood running through, and we could have external measurements on the blood oxygenation while having photoacoustic imaging and then comparing the results there. We could also develop more advanced machine learning models and develop more varied and physically representing training data. So that's it for my talk. Finally, I just want to say thank you to Vision Lab at the Cancer Research UK Cambridge Institute, and particularly Professor Sarah Bundick for this amazing opportunity to do this really interesting project, and Tom Els for supervision and training data, and lastly, Emma Brown for the in vivo data. Thank you.
Thank you very much for that talk, Helen. That was very, very interesting. And I think you've shown also that machine learning isn't just glorified statistics in the same way that physics isn't just glorified maths. The idea of skin phantoms is, completely new to me, and it's interesting to learn that, that's how the research goes about, and that's how we have to look at the data and, build that first kind of model. Before we go into the questions, actually, I just wanted to kind of, just remind everyone how amazing these two summer projects are that Helen and Pip have been doing kind of as undergraduates at the University of Cambridge doing in their summers. It's very impressive, really. It's kind of producing research and results that a lot of people would be proud of, really. So just to start to kick off the questions, we're having a lot coming through, but is it possible in any way to develop the method of linear spectral unmixing in order to overcome the assumption about the tissue depth?
I don't know if that would be linear spectral unmixing in that case, but so linear spectral unmixing is sort of also a way in itself to overcome the issue with the tissue depth. So the issue really lies in the fluence, which is the energy divided by area. Yeah, maybe that's a bit confusing, but yeah, so linear spectral unmixing is in itself an algorithm, and I guess it maybe could be done. I don't know if other methods could be developed, but I think that machine learning would be the easier way to go in a sense, because then the computer learns instead of people trying to get to the physics and maths of it.
Yeah, definitely. I think machine learning is good in that sense and has that kind of reputation. Another question that we've had come through actually is just talking about more advanced models and what other, how do you see the future of advanced models going?
So the models I used only make predictions on spectra from each pixel, and that loses the sort of spatial information, like where this pixel is in the whole phantom or tissue. So what could be done is to use whole slices of the phantom or even 3D bits. And for that, we could use convolutional neural networks, which are used for recognizing objects in pictures. So essentially using a picture of our phantom with the photoacoustic signal.
And those convolutional neural networks, how are they different? In what kind of ways?
Right. So that's a good question.
Yeah, a bit of a tough one, maybe.
Yeah, it's hard to explain. So instead of having these nodes with individual data points going in as the input, these convolutional neural networks, they take like regions of the picture at a time, and then you can have filters. So it's really hard to describe like this. Really need pictures to show.
Yeah, for sure. I'm sure our audience as well could perhaps go and look it up. But no, thanks for trying to explain it. It's kind of, as you say, maybe if there's regions and rather than looking specifically. Another question that's come through, would you mind giving some examples of common materials with a lipid coefficient of 0 to 3, which the question asker says are the values that you've used?
So the lipid coefficient, I think, is quite hard to evaluate generally. And the 0 to 3 was quite arbitrarily chosen to be just I guess, physiologically possible values. So I didn't do any research into like the actual lipid coefficient in actual tissue. So yeah.
And in terms of the prediction of regions that you showed in some of your later slides, you mentioned that you have to have a particular concentration of hemoglobin in order to do that. What about the regions that don't have those high concentrations, or are we not as concerned with those areas?
So the total hemoglobin that I used as a measurement to basically decide which region to use was more assessing the signal to noise ratio. And also because I'm predicting the blood oxygenation. So other areas, if we're trying to do tumor detection with looking at how blood vessels reform, well, not really interested in other areas, but also in a real case, we don't know which areas will have these. So it's not specifically the total hemoglobin, it's more the signal to noise ratio, and we could assess that in different ways as well.
Yeah, that's a good thing to consider. As you say, if you're looking at oxygenation, those are the kind of regions that you want to be looking at in any case. I think we've possibly got time for a couple more questions. There's a question here of saying, are there ways of nevertheless using lipid data in vivo?
Yes. So I could use this set of data and do predictions on them, but I tried, but the results weren't great. And as I mentioned, the lipids don't absorb as strongly as hemoglobin. For my head, I think it's about like a ratio of 100. So unless we can get really clear images with good signal on, especially on the lipids, I think it's difficult. But yeah, it's possible and definitely worth it in the future.
And speaking of that data, perhaps to wrap up as this final question, how do we improve the training data quality?
So, well, first off, it's we use simulated data, and that already is, well, different from real life data. But the point is, it's hard to get a large amount of data from actual mice, for example. But we could have simulations where there are more blood vessels. So we only had one in the middle and always at the same position. And that's not really representative of our bodies. So yeah, different shapes of blood vessels, different size of the regions, the background layers, and the vessel, for example. And we could simulate more noise as well.
Yeah, I think there's definitely a lot of kind of parameters to consider there, and definitely a lot of ways that it can be taken. Thank you again, Helen, for that really interesting talk. I've definitely learned a lot, and I'm sure that our audience has too. Thanks again to Pip for her talk. I'm now going to conclude by saying that thank you for joining us, and I hope that you can join us for tomorrow, day 5, which is the final day of Varsity Sci, which features talks on neurobiology, physical sciences and medical physics, and neurobiology again. Our keynote speaker is Dr. Rolf Apweiler, the director of the European Bioinformatics Institute in Cambridge. So to conclude, I'm going to hand over to Christoph, who will end the session. Thank you very much.
Thank you very much once again for joining us, and thank you to Garrett for hosting this session. And we hope that you will also be able to make various events hosted by both the Chemical Society and by BioSoc later on. And we hope that you'll be able to join us tomorrow for the final day of Varsity Sci, and especially for our keynote with Dr. Apweiler. Okay, we're done. Thank you very much, Helen and Pip, two